Hey everybody, and welcome to our lesson video for 5.4. Before we can move any further with solving quadratics and different techniques to do that, we need to talk a little bit about complex numbers. Because in Algebra 1, we would just stop when we couldn't solve a quadratic because we hit the square root of a negative number and we would just say no solution. But in Algebra 2, we're going to look much more at the complex number realm. In other words, we're going to use I as an imaginary number to more accurately represent solutions for quadratic equations. So we're going to start today by just looking at what is a complex number. And in order to do that, we need to talk a little bit about the letter I. So I in math is not a variable. Instead, it's defined as the square root of negative 1. And so you can have real numbers, which we've talked about a lot throughout your math career. So numbers like 3 or negative 4.72 or pi is a real number or e is a real number. Any of these, whether they're rational or not, they're still real numbers. Now, imaginary numbers would be something like 3i or negative I. An imaginary number is going to have the square root of negative 1 built into it. Or you could think of something like the square root of negative 2 would be an imaginary number. Now the square root of negative 2 is really the same thing as the square root of negative 1 times the square root of 2, which is really the same thing as I root 2, which again is an imaginary number. Now around all of this, you also have another set of numbers. And that set of numbers is what's called the complex number system. And complex numbers include both real numbers and imaginary numbers. And they're written in the form a plus bi. In other words, they have a real part and they have an imaginary part. So every number you've ever learned about since you began math when you were very young was a complex number. Typically, though, we were just ignoring the plus bi part and just looking at the real side of complex numbers. But now we're going to open it up to include the other half as well. So the first thing we're going to talk about is how you plot complex numbers on what's called the complex plane. And just as a reminder, we're talking about a plus bi. So this is the imaginary side, and this is the real side. So on the complex plane, we have a real axis and we have an imaginary axis. And this is not really related to the xy axis. It's just a real on one side and an imaginary on the other. So for example, if I wanted to graph 3i minus 4, I would go 4 left on the real side, then I would go up 3 on the imaginary side. And that would be 3i minus 4. Now, if I wanted to do 6 minus 4i minus 1 minus 4i, I would need to simplify that first. And if I distribute the negative here, we've got 6 minus 4i minus 1 plus 4i. In other words, we really just have 5. So that long thing is represented by a dot on the real axis at 5. Now similarly, we can do this last one as well. We've got 6 plus 2 minus 9i minus 8 plus 4i, which is really the same thing as negative 5i. So we would be looking at the imaginary axis and go down 5. And that would give us our point, negative 5i. So you can see that plotting on the real and imaginary axis isn't too difficult as long as you can remember which axis is real and which axis is imaginary. Now the next thing I want to talk about are the powers of I, because I has very special exponent rules that it's important that you know and are very comfortable with. So let's think about this for a second. If we have I to the first power, that is obviously just I, right? If we have I squared, though, this is where it starts getting really interesting. Because if you think about it, that's the same thing as I times I, or upside down I apparently. I times I, which is the same thing as the square root of -1 times the square root of -1, which, if you think about that, the result of that would just be -1 because the square roots cancel each other out. So I squared is actually just -1. Now I cubed we can start thinking about as just I squared times I because we know both of those. So that would be -1 times I, or in other words, that would just be -I. And then I to the fourth, we could think about that as I squared times I squared, which is just -1 times -1, which is just 1. And we can keep this pattern going, right? Like if I wanted to know I to the fifth, I would probably just think about it as I to the fourth times I, which would just be 1 times I, which would just be I. And if I wanted to think about I to the sixth, I would probably think about that as I to the fourth times I squared. And the reason I would do it that way is I to the fourth is so easy, right? I to the fourth is just 1. So 1 times -1 is just -1. And you might be starting to notice here that there's a pattern at play because we're starting to get some repetition. I to the fifth is the same thing as I to the first. I to the sixth is the same thing as I to the second. I to the 11th, I would just think about that as I to the fourth times I to the fourth times I cubed. In other words, it would just be 1 times -I, which is just -I. And what I'm hoping you're noticing here is that because I to the fourth is just 1, we can ignore all powers of 4, or all multiples of 4, prior to the value that we're actually looking at. So for example, let's say I wanted to look at I to the 70th. I obviously do not want you to think about it as writing out a whole series of I to the fourths. Instead, just think about the fact that every multiple of 4 is just 1. So in other words, I to the 68th times I squared, because exponents add, we multiply, right? So I to the 68th times I squared is I to the 70th. I to the 68th is just 1. So really we're just looking at I squared because we've just got 1 times I squared is -1, and so the result would be -1. So you should be able to tell me the exponent for any imaginary number as long as you know or can quickly derive these 4. You just need to know I to the first, I to the second, I cubed, and I to the fourth. And if you know those 4, you implicitly know all the rest as well, which is actually really quite cool. So the next thing we're going to talk about is how you multiply and divide complex numbers. Addition and subtraction is fairly simple because you can just combine like terms like you would normally. Multiplication and division are a little more interesting. And we're going to start with multiplication. And we're going to look at this multiplication first. So 8 plus 2i times 8 minus 2i. And from Algebra 1, you probably remember that you can multiply this using FOIL, right? And so we can do 8 times 8, which is 64. 8 times -2i, which is -16i. And then we can also do 2i times 8, which is 16i. And 2i times -2i, which is -4i. I squared, I apologize, because it's 2i times 2i. Now, the middle two terms here both have an I, or a 16i in opposite signs, so they're going to cancel out. And we're left with 64 minus 4i squared. Now, I squared, we already said, was -1. So really, we're looking at 64 minus 4 times -1, or in other words, 64 plus 4, which is 68. And I want you to notice something here. Notice that when we were done with this problem, all the imaginary numbers disappeared and the result was a real number. That's because this is a very special type of problem that I chose. When you have two binomials that are the same except opposite signs in the middle, those are what are called complex conjugates. And they're very important in math because they allow you to eliminate imaginary numbers. The result is a real number when you multiply them. And that's really important. We're going to use that a lot as we move forward because it's a way to eliminate imaginary numbers from a problem so that you can result in a real answer even if you're working with imaginary numbers. So we're going to look at another example of that here, and that's division of complex numbers. One of the rules for division, much like with radicals, you're not allowed to have imaginary numbers in the denominator of a fraction. They need to be eliminated. And you might have a guess already of where I'm going with this, because if you think about it, if you want to eliminate imaginary numbers, I just said that you need to multiply by the complex conjugate, right? And so I'm going to rewrite this problem down here. So 6 minus I divided by 1 plus I. I want to multiply by the complex conjugate, and I obviously need to multiply by essentially 1 in order to not change the problem. So I'm going to multiply top and bottom by the complex conjugate in order to do my division. And so the result of that is we're going to end up with, on the bottom, we would have 1 minus I squared. And you know that because the two middle terms have to cancel out. Or you can just remember the multiplication trick that we learned back in Algebra 1 when you have a plus and a minus. But basically it's just 1 minus I squared here. And then on the top we need to use FOIL. And we would end up with 6 minus 6I minus I plus I squared. And so if we want to simplify the top and bottom here a little bit, on the top we have 6 minus 7I minus 1, because I squared is negative 1. And on the bottom we have 1 minus negative 1 for the same reason. So really we're looking at 5 minus 7I over 2 as our answer. And this is a valid answer because it no longer has imaginary numbers in the denominator. So essentially we're rationalizing the denominator like we were last section, except we're doing it with imaginary numbers using the complex conjugate instead. So that brings us to the end of our video on 5.4. This analysis of complex numbers gives us the tools to continue to move forward with solving quadratic equations.